Okay, in this assessment, you had a couple of different tasks. One was to determine whether the material that has this data with the temperature versus voltage in this circuit is a pure metal or a pure semiconductor. So let's just first of all take a look at the circuit. We have here that there is a 1 milliamp current source, so that current source maintains a current in this loop of 1 milliamp. And there's a voltmeter that is producing these readings and some sort of temperature sensor that produces these readings. So for these temperatures, these are the readings in volts, and the question is whether this is a pure metal or a semiconductor. Okay, so the first thing that you might want to notice is, first of all, that you have voltage. And we have this material, this mystery material here, but we don't know pretty much anything about it except the voltage drop across the material. So what we could do is, from our equation, knowing this is a direct current circuit, V equals I times R, knowing that the I is 1 milliamp, we can compute the resistance. So we know that the the resistance is equal to the voltage divided by the current. So if we put the resistance here, what we could do is take the voltage in volts divided by 1 milliamp, and you can see that this becomes volts per milliamp is going to equal kilo ohms. So this is going to be in the units of kilo ohms. And what we have here is basically these same readings over here, 10.91, 4.915, and so on, 1.735, 0.5858. These are in now kilo ohms. So we have a relationship between the resistance in kilo ohms and temperature, and we could see that as the temperature goes up, the resistance goes down. So that should be our first clue that we're working essentially with a semiconductor, because in a semiconductor, as the temperature goes up, the resistance drops. Now the big question is, why does that happen? We know that in a metal that we have the opposite behavior. As T goes up, we have the resistance going up. So let's now turn to the equations that we have for conductivity and resistivity. So here are your equations. The three that I'm imagining that you'll understand, apply, and memorize. V equals IR, we've already used that one. We've got resistance is resistivity times length over area, and the resistivity is 1 over the conductivity. So the equations I was hoping you'd apply and understand are these down here, which link into these. So let's take a closer look at these equations. Okay, I want to highlight this equation right here that you might recognize just as generically describing the conductivity equal to the charge of the carrier, charge per carrier, times, and this is the sum here of the mobility of the holes times the concentration of holes plus the mobility of the electrons times the concentration of electrons. Now this equation is oftentimes generically written like this, that the conductivity equals Q times the drift mobility times the concentration of carriers. So this is the concentration of charge carriers. Oftentimes this is electrons. It could be holes. This is the drift mobility. And the Q is, of course, the charge per carrier. And the drift mobility refers to the fact that if, for example, an electron were in a material and then there was a positive voltage put over here and a negative voltage here, the electron would essentially drift in that direction. It wouldn't, go in that direction, but drift through a series of collisions and head in that general direction. And in fact, the drift mobility is the units of the drift mobility are odd. of course, we can rearrange it. It's equal to conductivity divided by N times Q is equal to, this is negative, ohms to the -1, centimeters to the -1, or meters to the -1, centimeters to the -3 times coulombs. So the units of drift mobility end up being centimeters squared per volt second. So they're kind of weird. In any case, this equation is generically true for a conductor or an insulator. And what's different between an insulator and a conductor is essentially this term, N. The mobility itself is a function of temperature. And of course, you can imagine that as temperature goes up, if this were an atom, the atoms start to vibrate more, larger displacement about the lattice. So the mobility actually degrades with increasing temperature because electrons collide with this, what appears to be a larger cross-section of a vibrating lattice atom. So mobility, we'll just write it like this, drift mobility decreases with increasing temperature. However, this N is the number of free carriers and is proportional to e to the negative e gap over kT, or actually over 2 kT for an intrinsic semiconductor. Now, let me just say a little bit of how we end up with this equation.